So, hi everybody. I hope everybody was fine, taking care of yourself mentally and physically. And so today we continuing our seminars. We have the pleasure to have here Tobias Moldenhauer. He is from Germany. He has got a bachelor's degree in physics at the University of Tübingen, and then later a master's degrees of physics in the same university. He spent 3 months as a research stay at the Eötvös Loránd University in Budapest, Hungary. And now he's, I think, in the second half of his PhD in physics at the University of Tübingen. So today he will talk about recycling planetary proto-atmospheres. Well, thanks for giving this talk, Tobias. And so the podium is yours, please.
Yes, thank you very much again for inviting me. I'm very pleased to show my results here. And as you can see, the title of the talk is rather short. It's just recycling of planetary proto-atmospheres, because I'm going to talk about the topic in general, but of course, with mentioning my results, of course, but just to present the mechanism of recycling in general, because I think it's a very important mechanism that will help us explain some things with exoplanets. First, some context. So here we have a graph that shows the currently discovered exoplanets. On the x-axis, you have the separation to the host star, and on the y-axis, you have the planetary mass that was measured. And as you can see, there are 3 distinctive groups emerging. So let me try whether I can find my mouse. So you have here the close to the host star with a rather, okay, let's start with this group. So close to the host star with a large planetary mass, the so-called hot Jupiters, so gas giants closely orbiting the host star. And then further away, you have the cold Jupiters. And then below those 2 groups, you have a large group, so-called super-Earths and mini-Neptunes. Those are closely orbiting rocky planets of several Earth masses. And now, depending on their envelope content, they're called either super-Earths or mini-Neptunes. But what you can see is that this group is very large. And now, even if you account for observational biases, super-Earths are still very common. So we think that about 1 in 3 solar-like stars have at least one super-Earth. Unfortunately, the Sun does not have a super-Earth, but nevertheless, super-Earths and mini-Neptunes are very common in the universe. Now, why is that a problem? Let's discuss how a gas giant forms. So when you have a planetary core, here denoted with MC, the rocky planetary core, it will accrete gas from its circumstellar disk and accrete an atmosphere. Now, if this atmosphere becomes comparable in mass to the core mass, then self-gravity becomes important and accelerates this gas accretion. Of course, that's a gradual process, but for self-gravity to become important and accelerate this accretion process, the atmospheric mass needs to be comparable to the core mass. And then due to radiative cooling, you have then Kelvin-Helmholtz contraction that then makes the atmosphere contract. Then you can accrete even more gas, which then gravitationally attracts more gas, and so on. And if you have a low opacity, then this process is fast enough to then suck up all the available gas in the orbit of the planetary core, and your planet will become a gas giant within the lifetime of the circumstellar disk. So this is the process that makes gas giants, called runaway gas accretion. And from one-dimensional simulations of this accretion process, we know that in order to avoid runaway gas accretion, so you need either a high opacity, or you need an additional luminosity due to the accretion of solids that counters the radiative cooling, or you need your planetary cores to form late, so a late stage formation of the core, or you need a significant gap opening. Now the problem here is that for each of those 4 points, you can easily make an argument that that's probably not the case. For high opacity, for example, you need dust, but dust will evaporate at higher temperatures that you find in a contracting protoplanetary atmosphere. And for the accretion of solids, you have to assume an accretion rate and so on. So there's then an additional mechanism in addition to those that were studied in 1D simulation, which is called the so-called recycling hypothesis. And the recycling hypothesis states that the low entropy atmospheric gas that has cooled, so the gas of the protoplanetary atmosphere cools, therefore you have a low entropy, and now this gas is being recycled with high entropy circumstellar gas. So you get fresh gas from the circumstellar disk that replaces the cooled gas from the atmosphere, and this then acts as a heating mechanism, which will prevent the atmosphere from undergoing Kelvin-Helmholtz contraction, and therefore halt this contraction process. And this process is only possible in 3D. And we need such a process to explain that we see super Earths and mini-Neptunes in such a high abundance. And to study this process, three-dimensional simulations are needed. And we did a so-called shearing box approach. So instead of simulating the whole circumstellar disk, we simulate only the region around the planetary core, which allows us to use a rather high resolution and therefore resolve up to the surface of the planet. And therefore, we don't have to use gravitational smoothing. So there's no smoothing there of the gravitational potential of the core. And the flow pattern around the planetary core is well resolved. And this then allows us to study this flow pattern very well. And what we see is, so here you have a sketch made by my colleague Andre Oliva. You have a sketch of this shearing box. Here in the middle sphere, you see that there will a flow develop around the planetary core. And then you still have the shearing flow if you go further away, so the gas that just orbits the star. And at the orbit of the planet, you have then these horseshoe orbits. Okay, so this is how the flow pattern around the planetary core looks like. And what we then observe is that gas is being recycled in the midplane. So in the midplane, through these horseshoe orbits, gas is being recycled with the circumstellar disk and also through the polar direction. But I will come to this in more detail in a second. Now this is just for you to have an overview, the sketch, how this recycling process comes about. And now to analyze the recycling effect, we want to isolate it. So what we do is we use a very low opacity, an artificially low opacity, so that it's definitely not the opacity that halts Kelvin-Helmholtz contraction. So the atmosphere can very easily radiate away energy and therefore contract. And we don't include any accretion of solids. And we also assume an early formation, so there's still plenty of circumstellar gas around. Yeah. So with these initial conditions, we make sure that that recycling is the only possible effect that prevents the planet from becoming a gas giant. And another important thing to note is that in order to measure the cooling rate, we use the entropy and not the temperature, because entropy only decreases, well, of course, unless you have shocks, but in the atmosphere we don't have shocks. unless you have shocks, then the entropy only decreases through radiative cooling and is unaffected by adiabatic processes like compression and relaxation, because quite counterintuitively, if your atmosphere cools and then contracts, then it's actually hotter afterwards. So by radiating away energy, your atmosphere can become hotter. This is why we have to look at the entropy and not the temperature. Just to mention this. Now I've prepared a video that shows what happens in a one-dimensional setup. So the blue line here is the entropy of the atmosphere, and the red line is the density of the atmosphere, and always compared to the initial state. So that's why the blue line starts at 0. So there has been no cooling in the beginning, of course, and the density starts at 1. So the initial density distribution. And now if we let the simulation in only one dimension evolve, we see that the atmosphere cools in the inner parts and continues to cool, and therefore the density increases. So you slowly have an increase in the density of the atmosphere, and the atmosphere continues to cool. And as you can see, this process just continues, okay? Can you see this, how the blue line continuously decreases and the red line continuously increases? Yes. I think this is very well visible. Now, if we switch to a 3-dimensional simulation, so there's nothing different here except for the dimensionality. So it's the same radiative cooling. It's the same opacity, same density. Everything is the same. It's just 3D instead of 1D. And don't be confused that this red line is no longer horizontal. It's because of the vertical stratification that's included. So this is the reason for this. But if we now let this simulation evolve in 3D, what you can see is it starts out similarly. So the atmosphere cools. And interesting. Yeah, I think it's quick. Well, so there was some hiccups with my computer. Can you still hear me? Yeah, I think
Yes,
so, right?
yes.
Otherwise,
yes, you can.
Okay. Yeah. So I hope you saw it nonetheless. So in 3D, this blue line eventually stops decreasing, and the red line eventually stops increasing. So we arrive at a steady state where the atmosphere no longer cools, despite its very low opacity and despite that we don't have any heating at the inner boundary whatsoever, so no solids are accreted. And now if we look at the mass inside the Hill sphere for those two simulations, the blue line is the 1D simulation and the orange line is the 3-dimensional simulation. Then you can see that in 1D, because the atmosphere continues to cool, it continues to accrete more gas, and therefore the atmosphere becomes more massive over time, as you can see here. But the orange line eventually becomes constant in time and enters a steady state. And again, the only difference between those two simulations was the dimensionality. So blue was 1-dimensional and orange was 3-dimensional. And this is how we can clearly conclude that recycling happens faster than the cooling of the gas. And therefore, gas hydrodynamics, in a sense, here trumps radiative cooling. And we truly have recycling occurring, and it's an important effect, which is also just on its own able to counter this radiative cooling and therefore counter runaway gas accretion. So again, now we want to measure this more, closely. for this, we use tracer particles to track the mass. So for every cell, we use a couple of particles that then represent the cell, and that way we can track where the mass is going. And if we now track the mass after this steady state was reached, then we can see that the blue line here shows after what time how much mass inside the Hill sphere is being recycled. So how much of this mass was replaced with fresh gas from the circumstellar disk. And we see that after just a couple hundred omega Kepler inverse, so approximately 300-400, almost everything in the Hill sphere is being replaced. And therefore, we can conclude that the whole atmosphere, so everything in the atmosphere, not just parts of it, is recycled at very short timescales. And this explains that steady state that we observed in 3D compared to 1D, where recycling is just not possible in 1D. So if you have only one direction, you cannot recycle the gas. It's just geometrically not possible. Also in 2D, by the way. So you need 3D for recycling to occur. To do this, to analyze this recycling in even more detail, we can now use a tracer fluid. So what happens there, we just fill the entire Hill sphere with a fluid that traces the motion of the gas. And then we wait for some time. And then after this, we look at the concentration. And a lower concentration then shows us that this region recycles at a shorter time scale. Yeah. So what this looks like for the for this simulation with a one Earth core in one Earth mass core in the center is like this. So at t = 0, you see the whole Hill sphere is being filled with a tracer fluid, and then after t = 50, you see that there's some inner region that's still very yellow. So this this region recycles very slowly. And then if we go to 200 omega Kepler inverse, you can now see that even this inner region is no longer yellow. So a lower concentration of tracer fluid. So everything eventually is being recycled. And you can now also see how it's being recycled. So the gas leaves through these horseshoe orbits in the midplane. And here's the side view. So the side view is the view you get if you look at the planet from the star. Okay? And what you see here is that this radius that we saw earlier, where everything has a significantly longer recycling time, also still works for this view. So the atmosphere is approximately spherical. So we just define this region of high recycling time as atmosphere, because of course there now is no longer, if you consider recycling, there's no longer traditional bound atmosphere. So all the gas is eventually being replaced, and therefore we cannot still uphold this traditional definition of an atmosphere, but we can still define it through the recycling time. We can say, okay, the region that has a very long recycling time we call atmosphere. And as you can see here, this region is rather spherical. But now if we look at the front view, so the front view is so now the planet is either moving away from you or towards you. Don't quite remember from which side this was plotted. And here you can see that now it's a bit elongated in the x direction, and this is because of the tidal forces of the star. So the atmosphere is a bit stretched due to the tidal forces of the star, but still approximately spherical. Now let's zoom into this, and here instead of filling the entire Hill sphere with a tracer fluid, we just fill a small shell around the planetary core with the tracer fluid. This yellow region you see here at t = 0. And now if we let the simulation evolve with only this shell filled with tracer fluid, we see that in the midplane, this the material that was colored moves outwards and then is eventually picked up here by the horseshoe orbit. But this inner region that was not filled in the beginning is still not filled, but if we wait a bit longer to 50 omega Kepler inverse, it gets filled again. So now how does that happen? Because from this picture, we can see that in the midplane, the gas is just slowly moving outwards until it's being picked up by the horseshoe orbit. But if we look, for example, from the side view, then we can see that fresh gas comes in from the polar direction. And so the gas in the atmosphere in general is very well mixed, because at T equals 50 omega Kepler inverse, you can't really tell that we only filled a single shell with tracer fluid initially. And what we also can conclude is that in the midplane, the gas moves outwards, and from the polar direction, the gas moves inwards. And now this whole atmosphere is being mixed, and eventually all the gas will be picked up by the horseshoe orbit and replaced with fresh gas from the circumstellar disk. So now, of course, the question is, if this recycling is so efficient, why do we still see gas giants? So there must be a point where this recycling becomes inefficient, and the gas has long enough time to eventually cool and contract to form a gas giant. So what can be possible factors that affect the recycling timescale? And of course, there's the optical depth. So what happens if we change the opacity of the gas? Then the headwind, because there's a pressure gradient in the circumstellar disk. Then the planet experiences a headwind, because the gas, due to this pressure gradient, moves at sub-Keplerian velocities around the star, and the planet does not. So the planet moves Keplerian, the gas sub-Keplerian. Therefore, from the point of view of the planet, you have a headwind. Now, this headwind, of course, could alter the recycling, and of course, the core mass. So what happens if we change the mass of the planetary core? And another factor is the dynamical timescale, which is determined by the separation. So this shearing flow around the planet is, of course, affected by its distance from the star. So, of course, if you go further out, for example, now the simulation that you saw was at 0.1 AU. If you, for example, go to Jupiter's or the Neptune's orbit, you can imagine that everything becomes way slower, because the gas moves slower, there's less shearing, and so on. Now, those four factors are we have to investigate. Let's start with the optical depth. So the middle panel is the tracer, is the recycling timescale calculated using tracer particles for the simulation you saw earlier. So the middle panel is the same simulation that you saw earlier, with a very low opacity of 10 to the minus 4. And then to the right, we have an even lower opacity, 10 to the minus 5. And to the left, we have a higher opacity, 10 to the minus 3. First, what can we see? Yeah, so if we decrease the opacity, the atmosphere becomes larger. Why is that the case? It's because a lower opacity results in more cooling, and more cooling results in an atmosphere that contracts, and this then results in a higher pressure. And since these atmosphere rotate at sub-Keplerian speeds, they're mainly pressure supported, and a pressure supported atmosphere can be larger if you have a higher pressure. So that's quite counterintuitive. So that the atmosphere, even though it contracts, it becomes bigger, just because the increased pressure. It's quite interesting, I'd say. But the most important part here is, if you look at the color of these three atmospheres, they're all the same. So the recycling timescale is not affected by the optical depth. Okay, so what this means is that the cooling timescale, which is determined by the optical depth, is completely independent of the recycling timescale. And since those two timescales work against each other, this is quite interesting. So it just means that if one of those two is shorter or longer, then that one will win. Now let's look at the effects of the headwind. So this is the same simulation you saw earlier, but with the headwind included. What does that mean? That means that the horseshoe orbits are shifted towards the star. Show you. So here you have the horseshoe orbit, and here the other one. And due to the asymmetry introduced by the headwind, these horseshoe orbits are shifted from the orbital, from the orbital direction of the planet a bit towards the star, and this then results, of course, in an asymmetric atmosphere. So as you can see, now the recycling through the horseshoe orbits is asymmetric. So this the leading horseshoe recycles less gas than the following horseshoe, and it's also results in an asymmetric atmosphere in general. But we will in a second analyze what this means to recycling. And another thing to notice is that the atmosphere becomes a bit smaller. So if you look at this purple radius that is displayed here, I think it's a bit hard to see on this figure, but it's smaller than it was previously. Now let's look what happens if the core mass is changed. So here we have now a 10-fold increase in the planetary core mass. So instead of 1 Earth mass, it's now 10 Earth masses. And as you can see, at first, of course, the atmosphere becomes much larger, even though the plot here is scaled with the Hill sphere. So the length units you see here are in Hill radii, and therefore, because the Hill radius is larger at 10 Earth mass core than at a 1 Earth mass core, the length units increased. But still, in these increased length units, also the size of the atmosphere increased. So this is quite interesting. But another thing one can notice here is that there's structure developing in the atmosphere. So earlier, the atmosphere was basically just one color. Now here we see, at least in the midplane, and now what we see here is that there's structure. So there are these spirals with a higher tracer fluid concentrations and a lower tracer fluid concentration, and the horseshoe orbits are no longer symmetric. And of course, the horseshoe orbits are also a lot wider. If you look at this horseshoe orbit here now, it's somewhere around this. Earlier, it was way smaller. And this is quite interesting. We'll also check in a second what this means to the recycling timescale. Let's first check out the side view of the 10 Earth mass case. So here we see that, again, things are very asymmetric. So if you look at it at 50 omega Kepler inverse, there's a bulge on this side, and at 200 omega Kepler inverse, there's a bulge on that side. That's just because the atmosphere is no longer one sphere, one homogeneous sphere, but it starts to wobble and it starts to become turbulent. Also, if we look at the velocity field in the 10 Earth mass case, then it's no longer constant in time. So if you compare snapshots, I think it's a bit hard to see on the presentation, but you just have to believe me. So if you compare the snapshot at 50 and 100, then the velocity field looks different. The arrows point in different directions. Also, then if you go to the 200 omega Kepler inverse here plot, and this was not the case for the 1 Earth mass simulation. So again, for the 1 Earth mass simulation, you get a neat steady state where the velocity field is constant in time. And now at 10 Earth masses, we see that the velocity field is no longer constant in time, but still we do observe a thermodynamic equilibrium where the temperature of the atmosphere eventually becomes constant in time and does not continue to decrease or increase. So there's still an equilibrium evolving where the recycling fully counteracts the radiative cooling. So now there's also the front view of the 10 Earth mass simulation. And as you can see here, the effect of the tidal forces of the star is even more pronounced. So if we compare this, the side view, to the front view, we can see that here it's much more elliptical because it's stretched in the x direction, which is the direction that points away from the star, and this is just due to the tidal forces of the star. And also something to notice is that you have this huge region above the core where also the recycling timescale is rather long. This is just because that the velocities there are rather low. Okay, now let's look what this means for the efficiency. So we have here the one Earth mass case. It's the blue line. The 2 Earth mass case, which we didn't look at in a tracer fluid diagram, and also the 5 Earth mass case red, which we didn't look at that closely, and the 10 Earth mass case, which we looked at closely, and the orange line is the case with headwind. Okay, so let's first start with comparing the blue to orange line. So the blue line is the standard case, 1 Earth mass, no headwind. And then if we turn on the headwind, then we go to the orange line. And what you observe here is that the tracer fluid concentration after, so all those lines are after 200 omega Kepler inverse, is slightly lower compared to the blue line. So what this means is that recycling becomes a little bit more efficient. So the recycling timescale becomes a little shorter if we include a headwind. And now let's compare the blue to the green line. Then you can see that the tracer fluid concentration is now higher. What does that mean? So this means that if we increase the core mass from 1 Earth mass to 2 Earth masses, then there's less recycling occurring. So the gas takes longer to recycle, i.e. Recycling is less efficient. We expect this, right? Because if you increase the core mass, then gravity of the core is stronger. Therefore, the gas should be more bound to the core. But now the very interesting thing that happens is if we go from the green line to the red line, because then all of a sudden the tracer fluid concentration drops a lot. Okay, so if even though we increase the core mass from 2 Earth masses to 5 Earth masses. And the reason for this is that from 2 Earth masses to 5 Earth masses, what you see is that the atmosphere becomes turbulent. Okay, and now this turbulent atmosphere is actually more efficient at bringing the gas to the horseshoe orbits. Okay, so if you have an atmosphere that mixes more strongly, then what you see is that that recycling becomes more efficient. And this transition region is somewhere between 2 Earth masses and 5 Earth masses at 0.1 AU. So we can conclude from our simulations here. And now, but if we increase to 10 Earth masses from 5 Earth masses, then we see the same trend again as from 1 to 2 Earth masses. So from the red line to the purple line, now recycling becomes again less efficient. Okay, to summarize this graph, headwind has little effect, so we can ignore headwind for recycling. And increasing the core mass makes recycling less efficient unless you're at this tipping point where turbulence sets on. Okay, so at that point, increasing the core mass actually makes it shortly more efficient for recycling. But then again, if you increase the core mass even further, recycling becomes less efficient. Yes, I hope this was clear. So in general, recycling is less efficient with a higher core mass, but there's this tipping point where turbulence starts to occur. Okay, let me summarize. So we saw that the whole atmosphere in 3D simulation recycles on very short timescales compared to 1D simulations where this is not possible. And even though we isolated this recycling mechanism, so there was no other heating mechanism whatsoever, we showed that the atmospheres did not eventually collapse to gas giant. So we showed that recycling is perfectly capable of preventing runaway gas accretion on its own. And yeah, so 1D models ignore this recycling, so we have to do 3D models here if we to include the full story. Another result is that the recycling is independent of the optical depth. So the recycling timescale and the cooling timescale are two independent timescales. And we saw that for higher core masses, there's less recycling unless you're at this one tipping point between 2 Earth masses and 5 Earth masses where this where the onset of turbulence occurs. And from all those results, we can conclude that there's no in situ gas giant formation possible at 0.1 AU because we made it really easy for gas giants to form, right? So we used a very low opacity. We tried out 10 Earth masses, very high disk densities and everything, and still the envelope mass stayed very well below what you need for runaway gas accretion to occur. And yeah, so if you're interested in more of those results, there's a paper submitted, as I said, and hopefully being accepted soon, and then you can read up on all of this. Thank you.
Thank you, Tobias. Very nice talk. Now we are open for questions or suggestions or comments. Anybody would like to make a comment or a question? Ricardo, por favor, please.
Hi, Toby. Excellent presentation. Very interesting. I would like to know more about your about the case when you have the turbulence around 5 Earth masses. I mean, did you follow closely where is the limit when the turbulence acts and when the turbulence disappears? Because it seems like it's around 5, but it's not clear, at least for me, where it goes with turbulence to no turbulence. And also, do you see any other effects of turbulence that is not related with recycling?
So yeah, for the core mass comparison, the only simulations that I ran were with 1 Earth mass, 2 Earth masses, 5 Earth masses, and 10 Earth masses, because these simulations actually take a really long time, because we have to evolve them until this steady state is reached, then enter this tracer fluid, and then have it evolve even further. So this takes, for each simulation, takes a couple months, actually. So six months or something, this whole process for one simulation. Of course, you can do this in parallel. Yes, but of course, then only afterwards, I noticed that you have this turbulence curve between 2 Earth masses and 5 Earth masses. Yeah, so if we wanted to know where exactly this turbulence starts to occur, we needed to explore this parameter space between 2 and 5 core masses in more detail. Of course, all I can say for now is that at 5 Earth masses, you have a turbulent atmosphere. At 2 Earth masses, you don't. Where exactly this occurs, no idea. Yes, and any additional effects of this turbulence? So things were rather similar. So, for example, if you look at the density, you don't see that anything weird is going on. So the density is still very smooth and everything. So because these fluctuations that I call the turbulence happen on time scales that are longer than the sound speed. So you also don't see this turbulence in the temperature. Temperature profile is very smooth. density profile is rather smooth. You really only see it in the increased recycling efficiency, because what you see is that the atmosphere mixes much better, and because of this better mixing, more material comes near the horseshoe orbits and is able to be picked up by them. Yes.
Oh, okay, thank you.
Thank you, Ricardo. Anybody else? Well, I have one question. I don't know how really important is it, but how about external effects? I mean, if you have a perturber or effects of migration of the planets, are they out of scale to this analysis you do, or are they somehow important at some stage?
Yes, so of course the simulations were local simulations, so that they did not include any global effects like migration or even that the density profile of the disk changes. So we kept the density profile of the disk constant, and you could think, not really gap formation at 10 Earth masses, but that it at least perturbs the density field of the disk a bit. But I think because of the very short timescales that this occurs at, so we showed that after a couple hundred omega Kepler inverse, this atmosphere enters a steady state. I think it's okay to neglect those effects. So at those timescales, migration and things don't really play a role.
It's very fast, so
yes,
the effects usually okay, good. Okay, good. Anybody else? Any further question or comment? So I think that's it. Thanks very much, Tobias. Very interesting.
Thank you.
And thanks for your time to contribute to our seminars.